Let's work on the first example. Let us have this function f of x equals 1/4 x to the fourth minus 2x squared. And we'll determine the intervals where the function is concave upward or concave downward, and then find points of inflection if there are any. To get us started, we need to find first and second derivative. So we'll work on finding those. The first derivative will be derivative of that expression, which gives us by power rule x to the third minus 4x. Then second derivative is derivative of the first derivative, so we use power rule again, and we arrive at 3x squared minus 4. And then remember, the theorem says that any point suspicious or any possible points of inflection will have either second derivative being 0 or second derivative not defined. So we find the places where second derivative is 0 or exactly the points where second derivative is not defined. First of all, we set 3x squared minus 4 equal to 0. We get that x squared is equal to 4/3. So take square root of both sides, and then rationalize the denominator, and we get positive or negative 2 square root of 3 over 3. Then, since second derivative is a polynomial, it is defined everywhere, so there are no points where the second derivative is not defined. So the intervals we're going to consider will come from the following picture. So everything to the left of negative 2 square root of 3 over 3, everything in between, and everything to the right of 2 square root of 3 over 3. So the intervals we're going to consider are those three intervals. And now let me rearrange everything that we need and come up with a table. So that's the first and second derivative, and we put the intervals into the table. So the interval negative infinity and negative 2 root 3 over 3. The point negative 2 root 3 over 3, the interval between negative 2 root 3 over 3 and positive 2 root 3 over 3, the point 2 root 3 over 3, and the rightmost interval 2 times square root of 3 over 3 up to positive infinity. Then we choose some test points. So it looks like negative 4 will be in this interval, 0 will be in the middle interval, and positive 4 will be in the rightmost interval. Then we put those test points into the formula for second derivative. Second derivative at negative 4 happens to be 44, after we use this 3x squared minus 4 formula. So we put 44 in here. And the good news is that this number is positive. And since it is positive, we can say something about concavity. Then at 0, the second derivative is negative 4. So put negative 4 in here, and it is a negative number. And at positive 4, the second derivative is positive 44, which is a positive number. So what conclusion do we have? Wherever second derivative is positive, the function is concave upward. So it's concave upward on the extreme left interval and extreme right interval. Wherever second derivative is negative, the graph is concave downward. And then moreover, wherever we have the change in concavity, we have the inflection points. So here, both of those, negative 2 root 3 over 3 and 2 times root 3 over 3 are inflection points. So this is an inflection point, and I guess that is an inflection point. So let me clean up this bottom and put the answer. So the function is concave upward on this interval from negative infinity to negative 2 root 3 over 3. Together with the interval from 2 root 3 over 3 up to positive infinity. Function is concave downward on the interval between negative 2 root 3 over 3 up to 2 root 3 over 3. And there are 2 points of inflection, negative 2 root 3 over 3 and positive 2 root 3 over 3. After we did all that hard work figuring out the intervals of concavity, let's have a look on this graph as it is. And so this looks like the graph of the function 1/4 x to the 4th minus 2x squared. What we can notice, we can easily see where this function is concave up. So roughly, let me change the color. So roughly from the left hand up to somewhere this point, well, give or take, this graph looks like an upright U shape, so it's concave up. See, it pretty much fits this profile, so it's concave up. Then between this point and, I don't know, somewhere here, it fits this upside down U shape, so it's concave down. And then the right piece, there is an regular upright U shape, so it's concave up. And in the middle it's concave down. I'm just trying to indicate that we can roughly see what happens to the graph, what happens to the concavity if we look on the graph. Let's work on another example. This time let's take function 2x to the 4th minus 8x plus 3 and find any open intervals where the function is concave upward or concave downward and points of inflection. So as usual, we find the first and second derivative. First derivative is derivative of 2x to the 4th minus x plus 3. We arrive at 8x cubed minus 8. Then we take that answer, do derivative of that, and arrive at 24x squared. Then we will look for zeros of second derivative, and for the points where the second derivative is not defined. First of all, we set second derivative equal to 0. We get 24x squared equals 0. That gives us x squared equals 0, which is the same as x equals 0. Then we note that second derivative is exactly a polynomial. So it is defined everywhere, and there are no points where the second derivative is not defined. So we end up with only two intervals, negative infinity 0 and 0 up to positive infinity. After that we build this table with the intervals and the x equals 0 value. So for the test points we can choose -1 for the left interval and +1 for the right interval. And then we put -1 into the second derivative, and we see that, well, let's see, second derivative at -1 is gonna be 24 times -1 squared, that's +24. So we see that the second derivative is positive at -1. Likewise, if x is +1, we get the same answer, 24, which is a positive number. That allows us to claim that the function is concave up on both of those intervals, because second derivative is positive. And x equals 0 is not a point of inflection in any way. So we can start writing the answer. So the function is concave up on pretty much everywhere. So it's concave up between -infinity, 0, it's concave up between 0 and +infinity. The function is defined at 0, so we're just gonna join all of that together into a single interval, -infinity to +infinity, and there are no points of inflection for this function. Now we completed this hard work of figuring out the intervals of concavity of this function, and we figured out that this function is concave up on all the intervals. So we can have a look on the graph. And what we easily notice, the graph looks like an upright U-shape, so roughly this is the upright U-shape all the way through, so it's everywhere concave up.